Title: The Economics of the Airbus A380's Downfall. Primary engineering angle: aviation/aerodynamics, efficiency, drag, scale limits. Opening hook: the failure. In February 2019, Airbus made an announcement that would have been unthinkable just 15 years earlier. Production of the Airbus A380 would end. No crash, no catastrophic design flaw, no grounding order, just silence from the order book. This was supposed to be the future of air travel. A 575-ton machine, 2 full passenger decks, over 500 people crossing oceans in a single aluminum and composite structure. On paper, it was more efficient per seat than anything ever built. So how does the most advanced passenger aircraft in history fail? Economically. Because aviation is governed by one uncompromising constraint. Fuel burn is proportional to drag lift-to-drag ratio times weight /text, fuel burn, /propto /frac, /text, drag, /text, lift-to-drag ratio, times /text, weight, fuel burn is proportional to lift-to-drag ratio drag times weight. And when you scale an airplane up, the physics do not scale the way your balance sheet wants them to. Today, we're not talking about nostalgia. We're talking about first principles, lift, drag, hub congestion, and why the A380's business case collapsed under the weight of its own assumptions. 1. The context. Why build a flying skyscraper? To understand the A380, we need to rewind to the 1990s. Air travel demand was exploding. Passenger growth was tracking roughly 5% annually. Major hubs like London Heathrow, Tokyo Narita, JFK were slot-constrained. You couldn't just add more flights. So Airbus asked a simple economic question. If you can't increase frequency, why not increase size? At the time, one aircraft dominated long-haul capacity, the Boeing 747. But Airbus believed the future would revolve around hub-and-spoke networks. Massive centralized airports funneling passengers into megajets. The bet was simple. More seats per flight, lower cost per seat, competitive advantage. And from a purely aerodynamic standpoint, scaling up should improve efficiency, because of something called the square cube law. 2. The physics constraint, the square cube law. When you scale an object up, volume and weight increases with the cube. Surface area increases with the square. In aircraft terms, weight grows faster than drag-producing area. That sounds good. A larger aircraft should, in theory, have better fuel burn per passenger. And in isolation, it did. Visual. Graph showing seat-mile fuel burn, A380 versus 747 versus 777. Per seat, the A380 was about 15 to 20% more efficient than early 747 models. So what went wrong? Because aircraft economics are not just about physics. They're about probability. 3. The economic assumption. Filling 500 seats. An aircraft is only efficient if it's full. A 180-seat plane flying at 90% load factor makes money. A 500-seat plane flying at 60% does not. And filling 500-plus seats consistently is brutally difficult. Why? Because passenger demand is not continuous. It's stochastic. Visual. Bell curve demand model for long-haul routes. Routes fluctuate seasonally, daily, even hourly. The larger the aircraft, the higher the break-even load factor. The A380 needed roughly 75 to 80% occupancy to achieve its promised economics. That's fine on Dubai to London, Singapore to Sydney, Los Angeles to Tokyo. But what about secondary routes? Suddenly, flexibility matters more than theoretical efficiency. And this is where aerodynamics intersects with airline strategy. 4. The aerodynamic reality. 4 engines vs 2. The A380 uses 4 engines. The Rolls-Royce Trent 900 or Engine Alliance GP7000. For engines mean more redundancy, more thrust, higher maintenance cost, more parasitic drag. Now here's the key. Engine technology improved dramatically in the 2000s. High bypass turbofans became incredibly efficient. And ETOPS regulations, which limit how far twin-engine aircraft can fly from diversion airports, relaxed. This allowed aircraft like the Boeing 777 and later the Airbus A380 to cross oceans safely with just two engines. Why does that matter? Because two engines mean lower fuel burn from reduced nacelle drag, half the engine maintenance, lower acquisition cost. Physics again. Each engine adds frontal area, increases form drag, increases fuel burn. Visual. CFD simulation comparing twin-engine versus quad-engine drag profile. The A380 was optimized for a world that assumed 4 engines were necessary. But engine reliability advanced faster than Airbus anticipated. 5. Airport infrastructure, the invisible cost. Let's talk about wingspan. The A380 has an 80-meter wingspan. That exceeds ICAO Code E airport specifications. Airports had to reinforce taxiways, widen gates, add dual jet bridges, modify runway shoulders. Visual. Side-by-side comparison of airport gate modifications. This wasn't just an aircraft purchase. It was infrastructure redesign. Only around 140 airports worldwide were capable of handling it without major upgrades. So airlines lost routing flexibility. Compare that to a 777 or A350, which can land almost anywhere long-haul traffic exists. Infrastructure compatibility is invisible in marketing brochures, but it shows up brutally in operating margins. 6. The hub-and-spoke gamble. The A380 assumed the world would consolidate around megahubs. Instead, something else happened. Point-to-point travel exploded. Thanks to efficient twin-engine aircraft, airlines could economically fly Boston-Barcelona, Manchester-Orlando, Perth-London. With the 787, passengers prefer direct routes. No layovers, no missed connections, no mega-hub congestion. The A380 was designed for Heathrow-level slot scarcity. But secondary airports grew faster than predicted. Air travel decentralized. And decentralization punishes very large aircraft. 7. The structural limits, weight and wing loading. The A380's maximum takeoff weight is around 575 metric tons. To lift that mass, L equals 12 rho V2 SCLL equals \frac 1, 2, \rho V squared SCL equals 21 rho V2 SCL. Lift equals half air density times velocity squared times wing area times lift coefficient. To lift more weight, you must increase wing area, speed, lift coefficient. Airbus increased wing area dramatically, but larger wings increase bending moments, increase structural reinforcement, increase weight. It's a feedback loop. Visual. Wing stress distribution diagram. At this size, structural mass becomes a significant fraction of total mass. You're fighting gravity with aluminum, and aluminum has limits. Even with composites, you hit diminishing returns. 8. The production complexity. The A380 was not just large. It was logistically absurd. Sections built in France, Germany, Spain, UK, transported via specially modified ships and barges. Visual. A380 fuselage section transport convoy. Its wiring harness issue alone caused years of delay due to incompatible CAD systems between facilities. This wasn't just engineering. It was geopolitical manufacturing. And every delay increases program cost. Development cost, 25 billion euros. To break even, Airbus needed over 400 aircraft sold. They delivered 251. That gap is the downfall. 9. The misconception. IT was too big. Size alone wasn't the issue. Cargo ships are enormous and economically viable. The problem is utilization rate. A cargo ship can wait days to fill. An aircraft cannot. Aircraft earn money per flight hour. If you can't fill seats consistently, your asset utilization collapses. The A380 wasn't too big physically. It was too big probabilistically. 10. The oil price wild card. In 2008, Oil hit $147 per barrel. Fuel efficiency became critical. Ironically, this should have favored the A380. But instead, airlines preferred smaller, more flexible aircraft. Why? Because fuel volatility increases risk. Smaller aircraft reduce exposure. A 787 can be redeployed to different routes easily. An A380 cannot. Risk management defeated raw efficiency. 11. The pandemic, the final blow. Then came 2020, the COVID-19 pandemic. Long-haul demand collapsed. Airlines grounded fleets. When traffic returned, it was fragmented, leisure-heavy, regional, unpredictable. Exactly the opposite environment the A380 was built for. Many airlines retired them early, except one, Emirates, because Emirates built its entire model around the A380's strengths. A mega-hub in Dubai connecting continents. For them, the aircraft works, but only under very specific conditions. 12. The verdict. Was it an engineering failure? No. Aerodynamically, the A380 performs beautifully. Its lift-to-drag ratio is excellent for its size. Noise levels were remarkably low. Passenger experience? Unmatched. But engineering success does not guarantee economic success. The aircraft optimized one variable, seat mile cost at high load factor. The market optimized another, flexibility and frequency. And flexibility wins in a probabilistic demand system. Final thought. Human ingenuity versus limits. The A380 represents a fascinating tension. Physics allowed it. Materials supported it. Aerodynamics justified it. But economics rejected it. Because engineering doesn't operate in a vacuum. It operates inside markets, regulations, infrastructure, and human behavior. The A380 wasn't defeated by drag. It was defeated by distribution curves. And perhaps that's the deeper lesson. You can overcome gravity with thrust. You can overcome drag with wing design. But you cannot overcome demand variability with optimism. In the end, the A380 is a monument to what we can build, and a reminder that viability isn't about what's possible. It's about what's repeatable.